So another hard problem today. Find median from data stream. Median is the middle value. If it's even, there is no middle value, and median is mean of two middle values. Implement the median finder. Okay, so initializing, add num, and returns median. Answers within 10 to minus 5 of the actual answer will be accepted. Well, basically what we would need to do is index the kth element of a ordered set, which we can do with like a tree, but since this is a middle element, we can also keep split it into half and have min q of the second half and max q of the first half of elements, and then we can pick based on if even, then we pick both, and if not even, then we pick the from first if we keep the first bigger. Okay, so I mean we don't need anything for initialization. Private, so we need two queues. So the default queue is I think max queue, so that will be the lower half, and then we need so that's a representation, and that's comparator of upper. Great, so we don't need to do anything for this. And when adding number, so what we want to do, if lower size, upper size, then we want to do lower push num, else up. Well, other cases just we push to lower and then lower is larger, so upper push num, great, and then find medium. If lower size, upper size, return a lower. Wait. I want min pq of upper. Okay, that works. And otherwise we want return double of, or I can do this maybe, lower top plus upper top divided by 2. This should do a type conversion into double, and having one operator double should do the conversion. If the divisor, we will see. Wrong answer, 2.03. Interesting. Lower has this, upper has this. So lower gets 1, upper gets 2, and lower gets 3. So lower top. Let's see. I'm calling it function. So now I'm debugging what's wrong. great. This is not good. If they no, this is not a good logic. What happens to the pushing? I wanna push to top every time or push to lower, and if it has lower push number, right? And now we push the what we want to do. Well, if I have a number and it is a larger than or equal to, so if num is larger than lower empty, not empty but lower top, right, then it has to go to the other one. Then upper push number, else lower push number. So I push here, and now while upper size, lower size, lower push, upper top, upper pop, and then finally we have while lower size, while lower size minus upper size is over 1, then we want to do upper push, lower top, lower pop. I think this should work. Still no. Okay, so lower is not empty. So lower is empty. So we push it here. And it's over 1. No. Okay, then we push 2. And what happens? Well, lower is not empty and number is also, we push it to top and their sizes are same, so nothing happens. I know what's the problem. Okay, this might work. Let's see. Okay, that's okay. 2 heaps. Intuition. For anyone watching this, if is anyone ever watching this and thinking to themselves, how is it possible that I came up with this in 1 minute? Because I've seen a similar problem, almost the same problem before. It was a long time ago, but the idea is quite simple. So let's keep 2 heaps, max heap for the lower half and min heap for the upper half. Let's, if we maintain an invariant such that after each add num call lower size of lower minus size of upper is more than or equal to 1. The median is either the top element of lower if they have different sizes, or there could be a problem with this, because if they call find median on before calling add num, then this will fail. Interesting. But I'm not sure what should be returned at that point, so or it's the mean of both of their tops. Approach: when inserting a new number, we first check in what half should it be inserted, i.e. if it's larger than all elements, the top element of lower, since it's a max queue, since it's a max heap. When inserting a new number, we first check in what half should it be inserted. That is, if it's larger than all elements, the top element, since it's a max heap of lower, it should be inserted into upper. Otherwise into lower. Now we just balance the heaps, but their sizes, but the following holds for their sizes: up lower size minus their absolute difference of their sizes. This is what a dog should formula did. Absolute formula of their sizes is less than or equal to 2. So the balancing will require O1 operations. Pop plus push O1 pop push operations. Okay. The equation holds of their sizes holds from the invariant. Either we inserted the element into lower when it already had one more element than upper, or we inserted the element into upper which had either one less for exactly the same number of elements. Time complexity is, I don't know, let's call it log n per call, where n is the number of elements in the combined elements already edit. O of n, where n is the, since we do O1 of push and or pop operations for each in each method, and each operation has a O log n time complexity, since it's a heap. Since it's a heap operation. O of n, where n is the number of elements inside of the two. I mean, log half is that is 1/2 time log, that's log 1/2 plus log n, and log 1/2 is like minus something, so it's very slightly under, whatever. Is the number of calls of num. Okay. Oh, I forgot to write. Note, we can use advanced data structures like trip to enable direct lookup of kth element in a ordered set. The code will be even smaller if we use a library. The time complexity will be the same, and the code and the size of the code will be even smaller if we use a library. Great. Update. And that's it for today. So my break from learning compilers for exam I have in 2 days. Today I was doing control flow, data flow analysis, like live variables with reverse must analysis, and then reachable definitions with forward may analysis, and available expressions with forward must analysis. Live variables are may, but in reverse, and their transition block function was f of x is equal to, for live variables used, union with x minus defined variables, and for the other forward it's generated intersectional or intersection or union x minus what? X minus killed. Okay, and then we have some lattice sets which have a domain, and then infimum, supremum, minimum element, maximum element, and ordering, partial ordering, and they have distributive properties, and they have to be closed under composition, and something else. They are monotone, and then we have a Tarski theorem of fixed point theorem for lattice sets, which says that given a domain or lattice set L and a function, monotone function f on lattice sets, there exists a fixed point P for which it holds that if we pass P as an argument to f, the answer for f is P, and then we use that for naive and iterative algorithms. The naive algorithm is a round robin, which initializes, let's say we do forward analysis, so we initialize to empty, and then we have the equation such that out of B is, out of a block is when the output of throwing in F, and then output is the intersection of or union of successor inputs, and then input is a union or intersection of predecessor outputs, and then the naive solution just always iterates through each block, recalculating it until something changes, but that is inefficient because sometimes we are calculating a thing which did not change in last iteration. So first we add every single block into work list, and then while it's not empty we take one out, we update its calculation, and if output change then we put the successors of that block inside since their input changed, so we put them back into work list. And then we can skip doing data flow graph for using syntax driven translation, or however this is called, which means that we use attribute grammars, attribute context free grammars directly to generate the functions for transforming input to output, because we need only gen and kill, and then we can calculate gen and kill, for example, when we have a sequence of statements, or when we have a if else statement, or even if we have a while loop statement where we have to do iterations. So that's what I was doing today, and I don't know how I remember every single thing out of it. But I'm really sick of it. I've been doing it for 4 days or 5 days or who knows how long, and I still have to do code generation, runtime environment, what that is, intermediary representation, code generation, and that's the second half of semester. And first half is some introduction, then you have lexical analysis of how you generate and parse tokens, and then you have syntactic analysis, which is LL1 grammar. So you have top down doing leftmost derivations, and then you have left right grammars, which can have like a canonic LR and LR, and so that's SLR, and then you have LALR, which is some merge of states from LR, and then you get states in SLR, and you do the same, whatever, and then you got, that's 2 presentations of 5, and then last one is syntax driven translation, which has some left recursion and synthetic attributes and inherited attributes, and oh my days. In 2 days you will know my grade from the exam. Goodbye.